Hello grade 12s and welcome to this video on the electrolytic cell. In this video I will discuss what an electrolytic cell is, I'll show you its structure, and I will use the decomposition of copper chloride to put things into context. Your electrolytic cell makes use of a chemical process called electrolysis. In electrolysis we say that electrical energy is converted into chemical energy, or we can say we use electrical energy to produce a chemical change. So one of the big differences between an electrolytic cell and a galvanic cell is that in the electrolytic cell, electrical energy is used to, or converted into chemical energy. So we use electricity to drive a chemical reaction. That is what is taking place here. At the bottom of your screen, we have a diagram of your electrolytic cell. Since we need electricity, we need to provide the electricity, and as a result, in your electrolytic cell, you will see a battery. A battery or rectified AC. Rectified AC, if I'm not mistaken, is just where we take AC and we use one direction of it so that we have a DC power source. Another thing that is different about your electrolytic cell is that everything is contained in one beaker. In your galvanic cell, we had two separate beakers, two separate electrodes. But here we have one beaker and no salt bridge at all because we do not need a salt bridge. Like in your galvanic cell, we still have an anode and a cathode. The anode is still where oxidation takes place. Remember, anox. And the cathode is still where reduction takes place. You should remember, red cat. But unlike in your galvanic cell, where your anode was negative and your cathode was positive, here we have that the anode is positive and the cathode is negative. When I mention things like these, you might start to panic because how on earth are you supposed to remember that in the electrolytic cell, the anode is positive, cathode negative, but it's the other way around in your galvanic cell? This is how you're going to remember. You're going to use the acronym PANIC. Okay, at the end of the year, all of my matrics are panicked because there's so much to do, such little time, so much work. So PANIC stands for positive anode, negative is cathode. This only works for your electrolytic cell, where of course your anode is positive and your cathode is negative. But if you can remember PANIC for the electrolytic cell, the last concept you learned for the year, then you just remember that in your galvanic cell it swaps around. The cathode in the galvanic cell is positive and the anode is negative. So just use PANIC, it will make your life a lot easier. Our electrolyte, as mentioned, is in one beaker, so flowing between your two electrodes, or rather we can say both of the electrodes are in exactly the same electrolyte in your electrolytic cell. These are some of the key features of your electrolytic cell. Take note of them. They are very important. I'm going to skip this page. It is in your textbook. And I'm going to go on to the decomposition of copper chloride as an example. Copper chloride the decomposition of copper chloride happens by using an electrolytic cell. One of the key features of this electrolytic cell is that its electrodes are unreactive. Unreactive electrodes simply means that the electrodes themselves do not take part in the reaction. They are just there to complete the circuit, to allow the charge to flow into the liquid and out of the liquid. That is what your electrodes are here for. Unreactive means they do not react. So types of unreactive electrodes that you guys will come across are carbon electrodes, specifically in the form of graphite. Graphite, like your pencil lead, is able to conduct electricity. Another type of unreactive electrode that you should be familiar with is the platinum electrode, like the one that was used in the standard hydrogen electrode. Platinum is an unreactive electrode. And in your copper chloride electrolytic cell, where we have the decomposition of copper chloride, we have unreactive electrodes. The way the cell works is that we take copper chloride. Copper chloride is CuCl2 because it is copper 2 chloride. My copper has a charge of 2 plus, so we need 2 chlorine ions since the chlorine ions have a charge of -1. So we need 2 of those to balance out the 2 positives from the copper. So this over here at the bottom, that is the structure or the empirical formula for copper chloride. In this electrolytic cell, the copper chloride is going to decompose into copper solid and chlorine gas. We basically decompose copper chloride, making use of an electrolytic cell, because copper is very useful to us and chlorine is very useful to us as well. So that is the purpose of this cell, to take something that is less useful and turn it into something that is more useful, depending on what industry you find yourself in. In some industries, you might find that copper chloride is more useful. Now, of course, once you take the copper chloride and you put it in solution, it's going to dissociate. Copper chloride is made up of a metal and non-metal. So it is ionically bonded and it therefore dissociates into copper ions and chlorine ions. And that is what you can see displayed in the diagram on your screen. This that I'm erasing, don't worry about it. I will explain it in a different video. For now, I just want you to realize that as part of our electrolyte, we have copper ions and chlorine ions. Now what happens is we take our electrodes and we place them inside of the electrolyte. We then connect the electrodes using wire to a battery or cell. So here's our battery or cell, our power supply. The electrode that is connected to the positive terminal of the battery becomes the positive electrode. The electrode that is connected to the negative terminal of the battery becomes the negative electrode, as you can see on your screen. What will now happen is that the chlorine ions, which are negatively charged, these ions are going to migrate, which means to move towards this positively charged electrode, because of course negative is attracted to positive. When they get to the positive electrode is the anode, and at the anode oxidation is going to take place. So each chlorine ion is going to lose its extra electron. Those electrons will enter the circuit and they will move towards the cathode. So they're going to move in the circuit. Our chlorine atoms that are left over, they are going to form chlorine gas. So if you are observing the cell in real life, you're going to see little bubbles forming around your electrode, around the anode. Those are chlorine gas molecules that are forming. Gas in solution gives you bubbles. Once that has happened, so we have our chlorine gas forming, we're happy with that. Their electrons, the extra electrons from the chlorine ions, they move to the other side where we have the negative electrode, the cathode. At the cathode, we have reduction taking place, red cat. So what will now happen is those electrons that were taken away from the chlorine ions, they are going to deposit themselves on the cathode. The copper 2 plus ions that were in the solution inside of the electrolyte, they will now make their way towards this negative electrode because positive ions are attracted to negative charges. Once they get there, the copper ions are going to gain the electrons. And when they gain the electrons, they will form copper solid. Copper solid is what is drawn in orange on this diagram. You're going to find that around your unreactive electrode, copper solid, so a whole lot of copper is going to form, and you'll be able to see that. Once you're done with the reaction, you will actually be able to scrape it off of your unreactive electrode. Okay, and that is basically the decomposition of copper chloride in solution. Some things to just remember is that the side, the electrode that is connected to the positive terminal of the battery, it becomes positive. The electrode that is connected to the negative terminal of the battery, it becomes negative. The positive ions in solution are attracted to the negative terminal. The negative ions in solution are going to be attracted to the positive terminal or positive electrode in this case. And there we're going to have a reaction taking place, specifically a redox reaction. To take things a bit further, I would like to show you guys the half reactions for this electrolytic cell. Even though everything takes place in the same beaker, we still have an oxidation half reaction, a reduction half reaction, and a net ionic equation. And we are able to do this using our head, so you can think about it, think of those oxidation numbers and come up with your half reactions or half equations. Or, ladies and gentlemen, you can make use of your table of standard reduction potentials. Again, I'd like to remind you, you must use table 4A, not table 4B. So in table 4A, we look for the chlorine gas. There it is. Then we are looking for the copper that forms. Remember, copper forms, but it forms from Cu2+. Be very careful. There's also a copper plus, just copper positive 1 ion. Be very careful when using this table. Looking at this, remember the chlorine ions form the chlorine gas. The copper ions form the copper solid. So the half reaction that we find at the top of our table, this reaction is where oxidation takes place. That's our oxidation half reaction. The one at the bottom is the reduction half reaction. Now, some of you might find this confusing because according to the trend that we spoke about when speaking of the galvanic cells, we said that the substances at the top are most likely going to be reduced because they are very good oxidizing agents. The substances at the bottom, they're going to be oxidized because they are very good reducing agents. But remember, guys, that inside of your electrolytic cell, we have a non-spontaneous reaction. So in this case, the substance towards the top is forced to be oxidized. The substance at the bottom is forced to be reduced because of the presence of our battery. We know from this table that it is a non-spontaneous reaction because if we go and take the product and connect them, we get a negative gradient indicating a non-spontaneous reaction. Remember, you can also make use of a calculation, so you can calculate this, the cell potential, and in this case you're going to get a negative cell potential. This indicates a non-spontaneous reaction. But back to what we came for, we were looking for half reactions so that we can write them down. Our oxidation half reaction is the chlorine ions lose electrons, that is oxidation, to form chlorine gas and electrons. The reduction half reaction is the copper 2+ ions gain electrons in order to form copper solid. Since the electrons are already balanced, we now can go on to write the net reaction. In this case, it's 2Cl- plus Cu2+. These are both aqueous because they're in solution, are going to form chlorine gas and copper solid. And this is your net equation for the reaction that takes place during the decomposition of copper chloride. Ladies and gentlemen, we've reached the end of this video. I want you to please go and take a look at the differences and similarities between your galvanic cell and electrolytic cell on your own. These are very important differences. This table is very important. Something that is, however, missing from the table is that in the galvanic cell, we have an exothermic reaction, while in your electrolytic cell, we have an endothermic reaction. An easy way to remember this is in your galvanic cell, or a galvanic cell is a battery, like your laptop battery or your cell phone battery. These tend to get hot, so exothermic reactions are taking place. In your electrolytic cells, on the other hand, we will find that the beaker will get cooler because those reactions are endothermic. I will leave it up to you to go through this table and to remember it. But beyond that, we are done with this video. Again, if you have any questions, please ask me about them sooner rather than later.